Countdown, we'll be ready to go. Okay. From current slide. All right, any questions on anything we did last time? And who we got here? Okay, have you just added the course?
I did.
Okay, what's your name?
Christina Glass.
Figure.
Christina Glass.
Glass?
Yes.
Okay. And is it C or?
C.
Yeah. Christina?
Yes.
And you go by Christina?
Yes.
Okay. Good. Welcome to the class. All right. Well, then, before we get started, let me give you a little bit of background about the class, because you've not been in one of my classes before, have you? Yeah, I didn't think so. Okay. Number one, everything's not set up yet, okay? Because this class started with 4 people, and I wasn't sure they were going to let it run, but some of them needed it to graduate, so I did get permission. So bottom line to that is, I wasn't, I didn't have everything done at the beginning of the term, so I'm still trying to catch up. So, the first class we went over the syllabus and probably got the research paper done too, talked about that. Yeah, and so basically, it's, okay. I record every class that I teach using this package called Screencast-O-Matic. It records everything I say with everything that's projected on the board simultaneously in sync so that you can view everything later. Now, it doesn't catch my arm waving. You don't get that at all, okay? So you can get the first 2 classes, but like I said, I don't have it set up. I don't have the link in Blackboard yet. If you're really good at YouTube, you can probably go out there and find them, but it depends on how much you want to look. I've never done searches through YouTube like that, but you can get to it. But I'll have those done. I'm hoping to get most of everything caught up either this afternoon. I don't have much time on Tuesday, but then Wednesday afternoon, I don't have a lot of time then either. But I'll try to get it done soon. I've got some time in the evening too that I can work on it. So I'll try to get that done. When I get it done, when you go to this class in Blackboard, are you familiar with Blackboard? Yeah. Okay. There's a bunch of blue tabs when you come to the home page of a class, and they scroll down. There used to be just a few, now they have so many. Near the beginning of that is one called, it has syllabus somewhere in the title. That's where I'm going to put the syllabus. It's not there yet. I've been working on it. I almost have it finished, but see, they've done so many different things with the books this term, I have to put in a whole bunch of mess about the books and other things. So I'll get that finished. I'll put the syllabus there. Then another tab or 2 down, there's something called Instructor Information and Office Hours or something like that. That's where I'll put my locator card, which shows when I'm on campus, off campus, in class, out of class, lunch, that kind of stuff, and which campus I'm on, that kind of stuff. Okay, that's there. Then somewhere down, usually still on the first page, there's something called Class Handouts and More. Well, the best place I could, they used to have one called Content, and that made a lot of sense. They don't have that tab anymore, so I put it under Class Handouts and More. I'll have all your PowerPoint presentations there in static form. I'll have your research paper instructions there. And also I'll put links that I've gotten that either I found over the years or other students have told me about that they felt helped them in the class. I'll put those links out there, okay? And then I'll have the one that says Math 227 YouTube videos. And when you click on that, you go to the playlist for this course. Now, this is the first time I've taught this course using this book. I've taught the course in I don't know how many books before this. 'This' This is a great book, okay? But it's the first time I've taught from this, so I'm still sort of feeling my way through this one. But on the playlist, you'll see it's almost full of things because I don't delete the last term I taught it from the playlist for a couple of reasons. One, it's happened more than once that we've come in and the server's not working. And if the server's not working, I can't record the class. I can't, I can't save it to anywhere. So that's why I leave all the old ones out there. Even though it may have been a different book, hopefully it's close enough you can follow the same material. Okay. Number two, this happened in the last year. Our administration forgot to renew the contract with Screencast-O-Matic. So it wasn't out there anymore, so I couldn't save it, okay? So that's happened. And then there's been a time or two when the whole entire system has gone down. Like the supercomputer link is, something happened with it, and you couldn't do anything. So because of that, I don't delete everything and start over every term. I leave all the things in there. So that means at the top of that, when you do get to the playlist, at the top of it is the old files from last term. The new files are always add at the bottom. So the first one we had was called syllabus. The next one, I don't remember what we called it, but there's two down there, and then today's will be the third one. And every time I add one at the bottom, I'll take off usually one at the top, if I can find the things that are equivalent to it. Okay? May not match up well, but it'll sort of. Okay. I think that's most of it. Okay. Now, technically we should have started, I believe, at 11:06, but several people said they felt like they needed to have cross products. So we didn't get to do that last summer when I was doing 126, and at least two of the guys were in 126 with me, so they wanted to continue where we left off. So we're in 11.4 in the text. Now, have you got a copy of the text, or are you going to get on this new Cengage Unlimited, or do you know what you're doing? Is it? Okay, yeah, because you're taking more than one course that uses the Cengage book. Yeah, that's a cheaper way to go. But you don't wind up with a copy of the book. You get an ebook, and then you can purchase, I think for just $8 or something like that, a copy, but you're not really purchasing, you're renting it for that term. So for $8, if you want a hands-on copy, you can rent that for $8. What's that?
I thought it was you're going to get to keep it.
Okay, I thought so too originally, but then I heard later it's just a rental. And that's why it's so cheap, because they get it back. That's what I understood. You can check at the bookstore and they can fill you in. But the latest I heard that was around. See, this is all brand new to everybody here. So we're just sort of feeling our way through it. Yeah, I thought you could keep it too, but you can't. Or it doesn't look like you can. See, these companies, everything they do, they're not going to give up a dime, even though it sounds really good. For $119, you get any book you're doing, but then you have to redo it every term. You have to re-rent it. They don't want their material out there. So now, about the ebook, from what I'm told, and I just found this out last week, I thought when you did Cengage Unlimited, then you had it unlimited. But no, you have to get some sort of code from me. Well, they didn't tell me that. So last week, this guy had sent us an email, any help you need, we'll be glad to help. We'll set up a course for you and stuff. So I emailed back and said, well, I need these courses set up. Well, then he emailed back late Friday afternoon after I'd already left and said, could you give me a call Monday morning? And so he didn't set it up Friday, which I had thought he would. And so I called him this morning. Well, I'm sort of new at this, so what? Yeah. So I had to tell him all sorts of stuff. And he said, well, I'll see. I'm sort of new at it, so it may take me a day or two. He'd only been there 2 months or something like that. So, but his first email, hey, just let me know. We're here to help you. I'll set it up for you. Well, if I can. That's what I found out later. So anyway, hopefully within hopefully by Wednesday, I'll know a code that you'll be able to access it. Sorry about that, but you should be able to rent your book sooner if you want it. Okay. Any other questions before we get going on this? All right. We were at the top of page 782. We're talking about cross products. And this is a use or application of a cross product. And by the way, now the one thing, I don't like the publisher. I don't like Cengage, even though they're ones doing all the books and stuff. But I do like this author. I think I mentioned to the others of you before. He has 3 features that I've never seen any other author do. Okay? The first of these, okay, at the end of every section, there are exercises. Okay? And the exercises, the odd number exercises, have the answers in the back of the book. Most books do that. Some are even, some are odd. A lot are odd. He does that. But not only does he do that, he has this package called calchat.com, calccat.com, that works out every odd number exercise, a tutorial help on every odd number exercise in the book. Amazing. Okay? And then selected odd number exercises, he also has calcview.com, calcview.com, which has more detail on how to work out those. I mean, just really okay. But that's right, you saw me after class. Okay, so you've added the class too. Brown. Right. Okay, so today's your first day. But you know most of the ropes, right? Okay. And one thing I forgot to tell you, there is a research paper due in this course too. So anytime this term you want to turn it in, sooner the better, okay? Any topic you want to choose on calculus has anything to do with applications, people, phenomenon, anything you choose. So calcview.com takes you further in certain things. Well, now the reason I got this started, and by the way, these are all free websites. Anyone can use them. You don't have to have the book, you don't have the code, you don't need anything. Go to the website. Okay? Certain of the examples, which number 2 I'm just getting started to do, it has a little blurb here. See, and here's the third website. LarsonCalculus.com. LARSON Calculus, CALCULUS.com. And that has an interactive version of this type of example. Now, they don't do all the examples that way, maybe one per section or something like that. Okay? And this is the one that's that way, so if you want more detail, you can get it. Okay? Now, find a unit vector. What do we mean by a unit vector? Unit vector. A vector. Say again? Okay, a vector is a line array, basically. But a unit vector, what does, any of you played the old card game that was Uno? Okay, when did you yell Uno? One card left, that's what it stands for, 1. So guess what a unit vector is? A vector that has a magnitude of 1. Magnitude of 1, that's a unit vector. So we're looking for a unit vector that is orthogonal to these 2 vectors, both u and v. So how do we get a vector that's orthogonal to both u and v? Say again? Okay. Okay? What you're saying might be working, but guess what? The easy way. What's the name of the section? Taking a cross product. Take a cross product of these two vectors. That will give you a vector that's orthogonal to both of these. That's what we did last time, remember? Oh, that was a week ago, wasn't it? Yeah, we've forgotten all that. Okay? And then that will give you a vector that's perpendicular. Then we just have to what we call normalize that and make it a unit vector. Okay? You remember how to do a cross product. Anybody? Okay. You do what's like a determinant. What's the top row? I, J, K. Oh, this was a long time ago. Y'all remember that, don't you? And then what's the second line? Second row? The components of your first vector, u. And those would be 1, -4, 1. Now, I said we're going to do like a determinant. We really aren't. I'm going to take off that row. Well, we are, but we're, okay. And what's the third row? Second? 2, 3, 0. Okay. Now, the easiest way, I think, to do a determinant of a 3 by 3 vector is to repeat the first two columns. Remember this? I, J, 1, -4, 2, 3. Okay? Now, what we're going to do is do your diagonals. Multiply this way, and what do you get? Second? 0. Okay? Multiply this way, and you get 2J. Okay? And multiply this way, and you get, if I could draw a straight line, plus 3K. Okay? But then, I'm going to erase those because I've got so many in there, they're hard to read, so let me get those out of there. Okay? Then we're going to do our up diagonals. Okay? And these are always negative of what you get. So what's the product that way? Okay, it's negative 8K, but we do the negative of it, so that's plus 8K. Okay? Same thing here, and what do you get? Negative 3I. Perfect. And this will be 0. So here's a vector that's perpendicular to both of these vectors, and that would be minus 3I plus 2J plus 11K. Okay. Now, by the way, you notice in the book, they put all vectors in bold, including, guess what kind of vector I is in J and K? What's that last card? Unit vectors. These are unit vectors in the X direction, the Y direction, the Z direction. The I is 1, 0, 0. The J is 0, 1, 0, and the K is 0, 0, 1. Those would be their components. All unit vectors. Okay? Now, the book just puts all vectors in bold. When I'm writing a vector, I put an arrow over it. Like if I wrote that, I don't write bold. You wouldn't be able to read it if I did, you know. So I put the arrow over it, meaning it's a vector. Unless I'm talking about a unit vector, and then I put the little caret over the top. That probably has a different name than caret, but that's what it is. So there is a vector that's that's perpendicular to both of those. Okay? That's the cross product of those two. How do I make that into a unit vector? You want to recall? Okay. Say again? Yeah, the magnitude has to be 1, and you're sort of getting close. Warmer, warmer. So what do? You determine the magnitude of this vector. That's going to be a number, right? Divide by that number. And then you're going to have a vector whose magnitude is 1. Okay? So, how do we get the magnitude of that vector? You want to give this a name? You don't have to, but you want to give it a name? Huh? X? That would work. So let's name this vector vector X. Okay? Usually X is along the X direction. I usually don't like that, but as long as y'all understand this has X, Y, and Z components, you're okay. You're okay with it? Not V, because we've already used V. Oh, B? Oh, that'll be fine. Why not? Okay? Let's call it B. Vector B. Okay? Whoa! That's not what I wanted. Okay. We'll call it B. Were you saying X before, or did you say A before? Before, when you said name it, did you say X or did you say A?
I said S.
X, okay, yeah, okay. B is better. So, to do the magnitude of B, the symbol for that is magnitude of B. That's the symbol for magnitude. Tell me how to get that. Anyone recall? Second? A little up. No, it's sort of like an absolute value in a couple of ways. Number one, always positive. So that's sort of the same, but not quite the same. Remember how to do a magnitude? Square root of -3 squared plus 2 squared plus 11 squared, which would be the square root of 9 plus 4 plus 121, which would be the square root of, what's that, 13 and 121, 144? Is that right? I'm doing it in my head. Huh? 134. You're right. Square root of 134. I was being too hopeful. Okay? Well, that's not a perfect square by any means, right? So, but here's what the unit vector B is. I'll give it a different name. Give me another letter. C? Is that what you said? Okay. We'll call it vector C, but that's a unit vector. That would be minus 3 over the square root of 134. I, if I could write, plus 2 over the square root of 134. J, plus 11 over the square root of 134. K. Okay? And if you don't believe me that that's a unit vector, square root of this squared. The square root would be 9 over 134 plus 4 over 134 plus 121 over 134, and 9 plus 4 plus 121 is 134 over 134. That's how you get a unit vector. And that should be perpendicular to both of those. This is sort of a trick question, but not really. Can you convince me tell me an easy way to say, yes, indeed, this vector, or you could use this one, but it's just easier without the square root of 134. This vector is indeed perpendicular to that. There's a real easy way. The thing before we did cross products, and this was last term in 126, we did dot products. Dot product is multiplication of two vectors, and a cross product is multiplication. There are two different kinds of multiplication of vectors. The cross product, the dot product yields a scalar number. The cross product yields a vector. Okay, like we got here. The easy way to check to see if two vectors are perpendicular, and these are supposed to be, is do the dot product. And this is a review now. The dot product, you simply multiply the components. 1 times negative 3 is, help me, negative 3. Negative 4 times 2 is negative 8. Negative 3 plus negative 8 is negative 11. And this is positive 11, and that adds a 0. The dot product of two perpendicular vectors is always 0. That one works. How about these two? Negative 3 times 2, negative 6, plus 6, 0, plus 0 is 0. Yeah. This is perpendicular to both of those, and when you normalize it, put it over its magnitude, it becomes a unit vector. So there we have it. A unit vector that is orthogonal to, or perpendicular to, orthogonal, perpendicular to, normal to, all those words mean the same, the two vectors in question. So that's how we did it. Let's see how they did it. Do I need to leave this up a little long? Okay. Okay. Well, the cross product, first thing they did the cross product this way. And they just showed you that's the answer. They didn't show you how they got it, but sure enough, that's what we got, right? Okay? And then that gives you a vector perpendicular to both of those, because the cross product is, by definition, perpendicular to both of those. And then we normalize it by finding the, and this is what I was going to do, but I was afraid you wouldn't understand the thing, the magnitude of the cross product, which is u cross v, would be square root of minus 3 squared plus 2 squared plus 11 squared minus square root of 134, and then just put that over. So it's minus 3 over 134, square root of 134i plus 2 over 1 square root of 134j plus 11. Just like we got it. All right. Now, let's continue with the cross product. And they're skipping example 3. How about less doing example 3? So let's go back and do example 3 here. The vertices of a quadrilateral are listed below. Show that the quadrilateral is a parallelogram and find its area. So here are the vertices. Vertex A is 520. Vertex B is, these are points by the way, 261. C, vertex C is 247. And vertex D is 506. Okay. Now, it says first show that it is a parallelogram and find its area. What does it mean to be a parallelogram? Second? Okay, there's two sets of parallel lines. I think that's what you're saying, right? These two are parallel, these two are parallel. Now, if it was a rectangle, they'd all be right angles too. But a parallelogram is equal, okay, and to be a parallelogram, well, these two sides would be, they have to be equal length and parallel to each other. What they don't have, the angles don't have to be equal. If they were, that'd be a rectangle. Now, all rectangles are parallelograms, but not all parallelograms are rectangles. So, to show that this is a, and by the way, the sides have to be the same length as well. So the parallel sides have to be the same length. Otherwise, it wouldn't be a parallelogram. It would be a trapezoid or something else. Okay. So, there's a couple ways you can do it. You could determine which of these are the parallel sides, and there's a couple ways to do that. But the easiest way would be, we haven't done three-dimensional slopes, so let's not go that way yet. It would be called a gradient, where that's later in the course. So for right now, how we can tell if they're parallel is, okay. Because not all of you were here, I don't want to assume that you know this. If you, oh, you don't have books. Okay, yeah. Okay, Theorem 11.7, which we did last time, said that any okay, actually it has two things in it. It's actually Theorem 11.8 is even better. Okay? All right. It doesn't say this explicitly, but I think we said it in class. Okay. In a dot product, two perpendicular lines, the dot product of them is 0. The dot product of two parallel lines is going to be the maximum length. It's just the length of those two added together. Okay. For a cross product, the cross product of two perpendicular is going to be your maximum value of the cross product, whereas the cross product of two parallel lines is 0. So, how we can determine if these are parallelograms, if we can find that two sets of these have 0 cross products, that means they're both parallel to each other. By that? Okay, so that's what we need to do first. So let's start off doing cross products. Okay? Now, they actually drew a picture for you, and that's nice of them to do. And if I could draw 3 space easily, I would. In fact, I guess I should, just to let you see what this is looking like. I hate doing this, but let's do it. I don't draw these well. Now, mine isn't as good as one in the book. This is going to be my X, that's going to be my Y, and that's going to be my Z. The reason I chose that orientation, it has to be a right-hand rule. X cross Y has to be 0, and that's what we got there. Okay, so let's plot the points in here. 5, 2, 0. So let's do 1, 2, 3, 4, 5. 2 on Y, so that's going to be something about here, 0. There's the first point, that's point A. I started to put it in parentheses, so I don't need to. That's just point A. Maybe what I should do is put its coordinates. 5, 2, 0. Okay, point B is 2, 6, 1. There's 2. There's 1, 2, 3, 4, 5, 6. So 2, 6 would be something about like that. And 1 up is somewhere there. Okay. I hate drawing 3-dimensional, 2-dimensional screen. It just drives me crazy. Okay. So this isn't the point. That's the point. So this is B, and that's 2, 6, 1. Okay. C is at 2, 4, 7. So 2 on X, 4 on Y, and 7 on Z. Okay, I have to draw this one in so I can count from it. That's somewhere about there. And then there's 1, 2, 3, 4, 5, 6, 7. Okay, somewhere that far above that point would be somewhere about here. So there's point C. Which is 2, 4, 7. And then D is 5, 0, 6. 5 on X, 0 on Y, and 6 on Z. 1, 2, 3, 4, 5, 6. Right there. There is D, which is 5, 0, 6. Okay? And sure enough, it kind of looks like that could possibly be a parallelogram. Okay, I hate writing these things. Okay, so what we want to show is that the vector between A and D, we want to prove that is parallel to B to C, right? Okay, how do we do the vector from A to D? So I'm going to write that this way. I'm sorry, I said D and wrote B. Okay. How do we write that vector? Now, in vector notation, I think this book uses it, though they seem to be using IJK notation much more frequently. Actually, we didn't have to do it this way, but it's fine. To do this, we pick either one of these and subtract the other one from it, okay? So I don't know if you want to do the vector in this direction or if the vector in that direction. Which way you want. I wrote it as if it's A to D. So that would be this minus this. So that would be 0, negative 2, 6. By that? 0, negative 2, 6. Those are components. Now, written in IJK notation, that would be minus 2J plus 6K. Right? This is component notation. Okay? Let's do BC similarly. And you tell me what that would be. 0. Negative 2. Second. 7 minus 1. 6. Hey, we don't have to do anything more. Those are exactly the same vectors, meaning same magnitude, same direction. We've just shown they're parallel. It's the same vector, right? So that was even easier than I thought. So we can do the same thing for those two. If those two turn out the same vectors, we know it's got to be a parallel, right? So let's do those two. You want to do DC or B or CD? I don't care. Pick one. DC. I was going to say that too. I like DC. Okay, DC. Now, what would that vector be? It's from D to C, so it's C minus D. So it's what? Negative 3. And that's a 4 minus. Oh, you're right. I was looking at the wrong thing. You're right. 4 and 1. Okay. Let's do now AB. And that would be negative 3. 4 1. Ding, 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 ding. Same vectors, parallel, same magnitude, same length, parallelogram, all over the place. Okay. Now the second part says, find this area. This is where we go back to the last, that last theorem, 11.8, and it says the magnitude of U cross V is the area of the parallelogram having those as the adjacent sides. Guess what? This can be our vector U, which is the same as this one. So those are the same. And this can be our vector V, which is the same as that one. So we'll just do U cross V. I just need more room. So where do I go? Let me erase some stuff here. What don't I need? I already have these points in there, so let me take them out, and I'll just erase my z-axis. I didn't mean to, but I did. Or part of the z-axis. Okay. Now I think I have room to do it. So let's do U cross V. And the magnitude of that is going to be our area. So what is U cross V? How do I do that? Determinant of, what do I put as the top row? I, J, K. Second row, 0, -2, 6. Third row, -3, 4, 1. Okay, I'm not going to put the other bar there because to do the determinant of a 3 by 3, I find easy to just repeat the first two columns. So that'll be a I, 0, -3, and a J, -2, 4. And then what do we do? Down diagonal, and that will give us a -2I. Next down diagonal. Second. I'm sorry, I can't hear you.
For the I, wouldn't it be 0 and 4?
Okay. Now you go to diagonal. -2 times 1. If I wrote it right.
The first number is 0.
Okay, yeah, but you don't use that. You do the diagonal. I, -2, 1. Multiply these two together, -2 times I. Next down diagonal. Help me. -18J. Okay, the last down diagonal. 0, I can do that one. Okay, now I'm going to take those lines out of there just to keep them from being so messy, as if I cared about messiness. Okay. Now we do the up diagonals, which are subtracted, and the first up diagonal is, second, -6K. Next up diagonal is -24I. I can't write. And the last one is 0. Okay, so what do we have? Now my writing stinks, so let me clean that up a little bit. Whoops, I cleaned it up too much. That was an I. Okay. So we have -2I and -24I. That's -26I. I'm sorry? For the K? Okay, wait. I'm sorry. I have a bad knee, so I get up slowly. Where are we talking?
Second floor, let's say
Negative 6K?
yeah.
Okay, it's up diagonal. It's a minus and a minus, I think, aren't they? Minus and minus. But up diagonals are always subtracted. Down diagonals are added. So yeah, it's opposite. So this is a positive 6, and subtract that would be a minus 6. K, and then that should be a minus 24I. Down diagonals are positive, up diagonals are negative. Okay? Now, when we combine those like terms, that would be, oh, there it is, minus 26I minus 18J. Why do they have such big numbers? I don't like it. Minus 6K. Okay? Because what's the next thing I've got to do? What did the theorem tell us? That's the cross product. This is U cross V. Now, I bet you if I had chosen going the other way or cross the other way, these would have all been positive. But guess what? Who cares? Because guess what we're going to do? Take the square root to get the magnitude of that. So let me started to write my equal sign here, and I realized I'd already written my equal sign. Okay. No, where is it? No. Yeah, no. Okay. So the magnitude of U cross V is going to be what? Remind me. The square root of, 26 squared. Oh, that's a minus 26 though, isn't it? Who cares? When you square it, it's going to be positive. So 26 squared, you pull out your calculators, you do the math. 26 squared plus 18 squared plus 36, take a square root of it, what do you get? 26 squared plus 18 squared plus 36, take a square root of that sum, and what do you get? Say again? Wait. Let me get ready to write the answer down. I wrote the square root. I don't want to write all that down. Okay, what is it? 1,000 what? 036. Okay, did you take a square root to see if that's a perfect square? I don't think it is. No, okay. That's it. That's the square root. So let's see how the book did. Okay? The square root of 1,036. Perfect. It's about 32 and a fifth or so. Okay. All right, so we did it. We showed first it was a parallelogram, that the two vectors making up the sides were exactly the same vectors. And then when we do a cross product of those two vectors and take the magnitude of that cross product, you get the area of that parallelogram. All right. Now, we're ready for the next slide. All right, to move on? Okay. In physics, yay, physics! All right. The cross product can be used to measure torque. I think we talked about torque in an earlier class. It's a lot like work, only different. Okay, it's the moment m of a force F about a point P. Okay, and I gave the illustration of a torque wrench. Okay, so if the point of application of the force is Q, so here's the point about which you're twisting. Okay, here's the point Q where you're going to initiate the twist. You put a force, it doesn't have to be perpendicular, they showed it almost perpendicular, yet some force on Q that's going to tend to twist it around here, and that's going to give you your moment, which is perpendicular to both PQ and F, and perpendicular to both, and the magnitude of that is going to be the amount of the torque. The magnitude of the moment measures the tendency of the vector PQ to rotate counterclockwise using the right-hand rule about an axis directed along the vector L. So that's what one application of a cross product is, torque. There are others, but that's one. Now, they skip example 4. So let's do example 4, and we'll do it on the same slide we used before. So I'll erase all that. And example 4. A vertical force of 50 pounds is applied to the end of a 1-foot lever that is attached to an axle at a point P, as shown in figure 1140. Okay? I'll try to do a somewhat of a replication of that. All right. Okay. I probably didn't draw that too well. Let me try to clean that up a little bit. Okay. They're saying this angle here is 60 degrees. That was given in the book. Your force is perpendicular to that, is downward force. That's a vertical force, F, of 50 pounds. Okay, now, if we let this be X, Y, and Z, that translates to a vector 0, 0, 50. Okay? To the end of a 1-foot lever, so the length here is 1 foot, so we have all sorts of units in here. This is 1 foot in length. Okay? That is attached to an axle at point P, and that's the origin is point P. It's shown in the figure. Find the moment of this force about the point P when theta is equal to 0. Okay? Now, it looks like to me, I think I'm safe to say this, that this is all in the YZ plane. There's nothing in the X direction here. So this is all pivoting this way. So if I had to have coordinates for this point here, and we know this is 1 foot here, what would be the coordinates of that there? Well, that's a 30, 60, a 30, 60, 90 triangle. And this is 1 foot. The hypotenuse is 1 foot. What would this side over here be? Anyone remember your trig? Jeremy and Justin, you better. I know you're a trig teacher, and he would be very upset if you didn't know that. Did you know it? Huh? Second? No, if the hypotenuse is 1, neither of the sides can be as much as 1. This side here is going to be exactly 1/2. Well, the short side of a 30, 60, 90 triangle is exactly half the hypotenuse, because the sine of 30 is 0.5. Cosine of 60 is 0.5. So this is 0.5. So the y vector, well, let's do a 3-dimensional vector. We need 3 dimensions. The x is 0 because there's nothing in the x direction. Okay, So that's going to be a 0. In the y direction, it's 0.5. And, ew, why am I doing that this way? And the z direction, that's going to be the square root of 3 over 2. Sorry. Okay, those are the components of that, which are also, coordinates of that point, which are also the components of the vector PQ. This is point Q up here, and that vector PQ is going to be PQ. The vector PQ is going to be 0, 0. Let me make it 1/2 since I'm doing the other in halves. Let's do that. 1/2 square root of 3 over 2. Okay? Now, the force is downward at 0, 0, 50. Okay? So, oh, I'm sorry, 0, 0 minus 50, because it's downward. Okay. So your torque is F dot D. Force dot how much is off center. So so let's do that. So the torque tau the moment, I like to refer to it torque. They like to refer to it as moment. So let's go back and change it to moment. Okay. The moment m, and that is a vector, is equal to PQ cross. I've always done it force cross displacement. They're doing it displacement cross force. I'm not sure I buy that, but they're going to talk only about its magnitude anyway. So let's do it. I, J, K, and we'll do PQ, which is 0, 1/2 root 3 over 2, and the K part is 0, 0 minus 50. Okay? Then let's repeat the I, 0, 0, and the J, 1/2, 0. Okay? Tell me what to do first. Yeah, down diagonal would be minus 25i next one 0, next one 0. Then let's do the up diagonals. Oh, already ahead of me. Okay, that would be 0, 0, 0. So your torque is in the I direction, but back that way. So F dot thing, it's back that way. I think they did them backwards, but it doesn't matter. So the magnitude is 25 foot-pounds. Now notice the term foot-pounds we used in work with a dot product. That's a scalar quantity. Work is a scalar quantity. Torque is a vector quantity. Still has the same units, foot-pounds. Feet times pounds, foot-pounds. Okay, that was example 4. All right. I'm sorry. My head is clogging up on me. I'm having trouble breathing. So, sorry about that. Okay. Now we go to another concept here. It's a use of a cross product. It's called the triple scalar product. The thing that doesn't sound cross in there is scalar, because cross products are usually vectors. So what are we meaning here? All right. Here we have three vectors, u, v, and w, in space. The dot product of u and the cross between v and w, that will give us a scalar number, because the dot product of two vectors is scalar. Now this cross product will give us a vector, then a vector dotted with another vector gives us a scalar, and sure enough, that's why it's called a triple scalar product. You use three vectors, but one's a dot, the other is a cross. The cross product produces a vector, and then the dot with the vector produces a scalar. So it's a triple scalar product. And here's what it tells us. Let's say u is equal to u1i plus u2j plus u3k. V is v1i plus v2j plus v3k. Those are called components of the vectors. W is w1i plus w2j plus w3k. Those are three components of that vector. For the triple scalar product, the thing you do differently here, what you would have done is ijk with v and w, and then you would dot the i's with the i's here and the j's. Well, as it turns out, you just put the u's across the top, components across the top, the v's here, the w's here, just in the order they're given. You just let the u replace the ijk, and now you're doing strictly a determinant, which a determinant is always a scalar value. See, before these were vectors up here, so that produced a vector. Now they're components, which is just the other, and sure enough, that will give you your triple scalar product. Okay? Now, something that I don't know if you realize or not, if vectors u, v, and w do not lie in the same plane, then this triple scalar product, u dot v cross w, can be used to determine the volume of the good old parallelepiped. Isn't that a nice word? A parallelepiped. That's a polyhedron, meaning a many-sided figure, all of whose faces are parallelograms. Every one of the faces is a parallelogram. This is, that is, that is, that is, this is, and that is. They're all parallelograms, with u, v, and w as adjacent edges, as shown here. So this is going to give you a volume, which is a scalar quantity. Okay. Now, they're showing here the u is a long vector. It doesn't have to be. They're just showing it this way. That's the one that's dotted with the other two. And if the other two, v and w, are down here, made so in the right-hand rule, so that component's up, generally in the same type of direction as u, though it's not exactly the same. What you've got here, the first thing you have here is projection of the cross product here, which is a vector here, the gray vector here, onto the vector u, or the vector u projected onto v cross w. That would be that projection right there. Okay. The area of this parallelogram on the bottom is the magnitude of this cross product, just like we did before, and the volume would then be that height, which is projection of that on that, times the area of the base, which is the V cross W. Okay? And that's why it comes out being the value of that parallelepiped. Pretty sounding word, hard to say sometimes. And they have a note here that I'm not sure y'all are familiar with, but let's see. Well, my head's hurting. Okay. Here's the deal that they are talking about, but they don't tell on the slide set. It is conceivable that this could come out being a negative number. Okay? Those dot products don't have to be positive. If it does, flip the order of two of these. Okay? Because in a determinant, and y'all shouldn't necessarily know this, in the determinant, if you change any two rows or columns, either one, you're going to negate the value of the determinant of what you had to begin with. So if this comes out negative, flip any two of the rows. Because guess what? If you use this as the base and then this is the, you can get the volume is the same no matter how you lay that down. Okay? So you could use anything as the base and anything as a height, you might say, of that. So you could exchange any two rows or columns. It still come out with a volume. So if when you do it the first time, if you get a negative number, just multiply it by -1 and you get the second part. Okay. So here's the geometric property of the triple scalar product. The volume V of a parallelepiped with vectors U, V, and W as the adjacent edges is, and how do you take care of the minus sign? Do an absolute value. Because remember, this is a scalar number. That's a vector, dotted with a vector, gives you a scalar. If that comes out negative, take the absolute value off, and you got the value. So there's the application for this. Let's see if they give an example. Yeah, here it is. Find the volume of the parallelepiped shown in this figure here, 1142. Thank you that I didn't have to draw that. Okay, having U of 3I minus 5J plus K. That's that point. V is 2I minus 2K, which is down there. And W is 3I plus J plus K. And frankly, it drives me nuts, but I do not think those are proper, okay? If this is your X this way, and there's your Y that way, and there's your Z that way, 3 on X would be, yeah, okay, those may be okay. Minus 5 on, yeah, it's all right. I was looking at them backwards. Plus 1 on K, then a 2J minus 2K, you do nothing on X with just 2. Yeah. 2 on Y minus 2 on J. I mean, Z. And then W is 3 times I, which is coming out here. That's the part that is bothering me. That doesn't look like it's 3 out. That's 1, 2, 3. Okay. So what they must be doing is 2, 4. So that must be 3 because they got the same 3 there. But then on Y, 1, 2, 3, 4, 5. I don't know. It just doesn't look like their scaling makes sense. It seems like to me both of these need to be further out here. This one here and this one over here somewhere. Okay? The ones on the K's are okay. That's a minus 2 on K. Okay, now that looks way too low here, but that's because of foreshadowing. It's so hard to see three-dimensional on two-dimensional plane. It just drives me nuts, but I just don't see that being three on the X direction for either one of those. I'm sorry, it just doesn't look right. Okay, but I'm glad they drew it and I didn't have to. We don't need to do it. So find the volume. So what do we do? The volume, well, just put capital V is equal to, I'm just going to do straight to the parallelogram. I mean, straight to the determinant. So my top row is going to be 3 minus 5, 1. Second row, second, 0, 2, negative 2, and third row, 3, 1, 1. That's a good defense. No, it's not. Okay. And then repeat the first two columns. 3, 0, 3, and negative 5, 2, 1. Okay. Then do your diagonals. And what do you get? 6. Second, plus 30. 0. I can do that one. Now let's do the up diagonals, and just to keep it from being so crowded, let me go and erase these 3 here. We're going to subtract the up diagonals, so that would be a minus 6a, and that would be a plus 6, and this would be a 0. Okay, well that would be 36. It's already positive, so we don't have to take the absolute value. That should be the volume of that parallel pipe, 36 square units, or cubic units, whatever they are. Okay, let me erase this and see what they got for an answer. It should be the absolute value of U dot V cross W, and that would be 3, negative 5, 1, 0, 2, negative 2, 3, 1, 1. And now they do it another way, which is perfectly fine. Do you want me to show you that way too? Or are you happy with the other way we did it?
This one is confusing. We want with the other one.
Okay, I like the other one too. But there is a way. We did it, I think, the other day, but it's a little more convoluted. Okay? And let's see what they get as an answer. Ah, look at that. However they get it is 36. Good deal. All right. Then there is a little consequence. A natural consequence of theorem 11.10, which is the geometric property of that, is that the volume of parallelepiped is 0 if and only if the 3 vectors are coplanar. So guess what? If these 2 vectors are parallel to each other, then the cross product is going to be 0, and that would work. If those 2 are parallel to each other, and that's 0, a 0 vector there, then you dot that. So that would be one thing. The other would be if this one's perpendicular to the cross product of those, and the cross product of those is parallel this way, for that to be is perpendicular to both of those. If this is perpendicular to both, it has to be in the same plane. So sure enough, it does work that way. Okay? If and only if the 3 vectors are coplanar. That is, when the 3 vectors have the same initial point, they lie in the same plane, if and only if that triple product is 0. Okay? But they would be in the same plane. All right, they don't do anything with it. Okay, 11.4, homework. Do either 3 or 5. They're both in calcchat.com. Do either 7 or 9. They're both at CalcChat. 7 is at CalcView. Do either 11 or 13. They're both at CalcChat. Do either 15 or 17. They're both at CalcChat. 15's at CalcView. Do either 17 or 19 or 21. They're both at CalcChat. Do 23. It's at CalcChat and CalcView. Sorry. Do 25. It's at CalcChat, but not at CalcView. And then do your choice of applied problems, 27 or 29. You choose. They're both at CalcChat. Then do either 31 or 33. They're both at CalcChat. 31's at CalcView. Do 35. It's both at CalcChat and CalcView. Then do 37. It's at CalcChat, but not at CalcView. Then there's an exploring the concepts. You can look at 39 or 41, do them if you wish. If you don't have to worry with them. And then there's a couple true false, 43 and 45. They should be at CalcChat. I don't know if they are, but they should be. And then there's a proof, several proofs. You can do any of 47 through 51, okay? One or more of those, and you should be able to do them fairly easily just with a cross product, okay? There's a couple more proofs, 53 and 55, and you can do those two if you wish. All those should be at CalcChat. Okay, I think that's the last slide. Yes, it is. My word. For some reason, I'm just completely running out of steam. But let's move on. If I had a little more time to go, I would run down and get a swig of some caffeine. I ate a little bit of salad for lunch, but that was all. I'm not, my blood sugar, I think, is really, really low. I didn't get to eat the rest of lunch. Why am I not? There we go. Let's get out of 11.4 and move on to 11.5. Okay. Okay. All right, 11.5, Chapter 11, Vectors and Geometry of Space. 11.5 is Lines and Planes in Space. And again, we're going to try to go through these fairly quickly, though I'm not doing anything quickly today. Write a set of parametric equations for a line in space. That's the first objective. I think you'll find it's a fairly simple thing to do. Write a linear equation to represent a plane in space. And I think you'll find that's not too bad either. We'll sketch a plane given by a linear equation. You start sketching things in space, that's not that bad, but boy, it can be frustrating, okay? And find the distances between points, planes, and lines in space. Sounds like there must be some little trick to that. Let's see what we're... Let's start with lines in space. All right, here's the setup here. What we have is a line. Here it is, this line L, just taking off through space here. Goes through these 2 points, P, which is x1, y1, and z1, that's the fixed point here. And it also goes through some other point out here, Q, which we're going to give variable components, x, y, and z. Okay? Now, we're going to have a vector down here leading from the origin, that the vector, and remember, not all of you were here before, so let me say it again. I've been doing it today, but if you weren't catching what I was doing. Points are given coordinates. We're going to live in free space most of our time, okay? So don't worry about in space and 7 space, or occasionally we may go to 2 space, which is the plane. Most of the time we're going to be in 3 space, which is okay. And any point in 3 space will have 3 coordinates. Points are identified as being parenthetical, okay? And they're ordered triplets, X, Y, Z, okay? The order matters and the values matter, okay? There's got to be 3 of them for the X component, the Y component, and Z component, okay? So any other point is going to have parentheses. A vector, on the other hand, these are called components of a vector. Coordinates of a point, components of a vector. And these are in the X direction, the Y direction, the Z direction. But notice I said directions. The coordinates are just numbers. The components are just numbers, but they indicate directions. Okay? So here's a vector V, A in the X direction, B in the Y direction, C in the Z direction. Now this indicates that it's positive on X, more positive on Y, and somewhat positive on Z to get it to that point here. All right, now, what we want to consider a line through some fixed point P, X1, Y1, Z1, so the subscript indicate fixed point, parallel to the vector ABC, and we can put our vectors anywhere in standard position, initially at the origin, initial point at the origin. And A, B, C are the components of that vector out in the X direction, Y direction, and the Z direction. So the vector V is called the direction vector of that line that determines the direction of the line. And the A, B, and C are direction numbers. Also components of that vector V, but direction numbers. One way of describing that line L is to say that it consists of all the points Q, X, Y, Z, that's why they're variable, they can be any point, for which the vector PQ is parallel to V. The vector PQ is parallel to V. So therefore it has to have the same direction as V. It doesn't have to have the same magnitude, but it has to have the same direction. Okay, that's the key. All right. Now, that means that PQ is a scalar multiple of V. It means it's in the same direction, but just scaled differently. And you can write PQ is equal to TV. That's not television. It's just the scalar T times the vector V. And that scalar means just a multiple. If PQ is longer than V, then this is a multiple greater than 1. If it's shorter than V, then it's a scalar less than 1. If it's an odd direction, it's a negative number. So it's a T is a scalar, a real number. Also called a parameter. Okay? Dr. Bryant, you can close that door if my talking bothers you. Okay, so what we're saying here is then that PQ, that vector from P to Q would be, and remember how we did that. Let's go back here again. Remember, if this is a vector of point P and Q is somewhere here, and you want the vector in that direction, what we do is this component minus this one, comma, this component minus this one, this component. That's how we define a vector. 2 points. The initial point terminal, always terminal minus initial, final minus initial, okay? X minus X1, comma, Y minus Y1, comma, Z minus Z1, comma, in angle brackets, that would define the vector, okay? So let me go and just write that here. I think that would make more sense. Let me get my pen color back. So this would be the vector PQ would then be vector notation x minus x1, comma, y minus y1, comma, z minus z1. Close out. Okay? Because that now makes it a vector. Initial minus final, final minus initial in each of the components. Okay? And that's equal to PQ, which is some parametric multiple of V. Okay? And that's exactly what the next equation says. That this is equal to AT, BT, CT. ABC were the components of V, and you're multiplying by that scalar number T. Okay? Now, by equating the corresponding components, you obtain the parametric equations with the parameter T that would do it for us. Okay? So notice what we have. X minus x1 is equal to AT. Y minus y1 is equal to BT. And Z minus Z1 is equal to CT. Okay? Well, if you wanted to, you could rewrite this as X is equal to X1 plus AT. Y is equal to Y1 plus AT. And Z is equal to C1 plus AT. Or you could write this as AT plus X1, whichever way you see this. That's a B, that's a C. Sorry. BT plus Y1 CT plus C1. Okay. Either one of those will work. Those are your parametric equations then. Your x, y, and z written in terms of the point x1, y1, and z1 and the components of the vector a, b, and c. Vector v, a, b, and c. Okay? And they wrote them this way. Let me clean up my ugliness there. Okay. That's a T. I don't know how it got so ugly. It's a B. They wrote it this way. That's an AT. Okay. Those are your parametric equations. Pretty straightforward. Parametric, okay. Here they are. Parametric equations of a line in space. A line L parallel to the vector V, ABC, passing through the point x1, y1, z1. Represented by the parametric equations x equals x1 plus AT, y is equal to y1 plus BT, and z is equal to z1 plus CT. Now, I don't know if this is helpful or not, probably not, but you can think of this as being, okay, there's the x component in space, and A gives you what direction from that x it's going and how fast. In other words, like slope-intercept. This is where it's starting and this is where it's going. And in the y direction, the same thing. Starting at y1 and taking off how big or small b is in that direction. And z, same thing there. If the direction numbers, a, b, and c, that's why they're called direction numbers, are all non-zero, then you can eliminate the parameter t in the parametric equations to obtain symmetric equations. Parametric to symmetric. Okay, so if all the A's, B's, and C's are not zero, all of them are not zero, then you can eliminate the parameter t. In other words, make this x minus x1 over a is equal to t, y minus y1 over b is equal to t, z minus z1 over c is equal to t. So you see that's why a, b, and c can't. None of them can be 0. And then this is what you get. X minus x1 over a is equal to y minus y1 over b, z minus z1 over c. Those are symmetric equations. I'm not sure why they call them symmetric, but they are. All you did was eliminate the t. All 3 of those are equal. Okay? Now, have we got time? Yeah, I think so. Find the parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4, parallel to the vector v, which is 2, 4, negative 4. Okay? So you want to come up with the, you tell me what to write to get there. Second? Well, the first thing I would do, okay, you need some x, y's, and z's, so let's use them. X minus 1 is equal to, isn't that your equation? That from your components, the point somewhere out there, x, y, z, x minus 1, that's equal to 2t. That's going to be multiple of this, scalar of that. That's the easiest way to remember. And give me the next one. Y plus 2 is equal to 4t. And z, second, minus 4 is equal to minus 4t. Okay? Now, those aren't quite our parametric equations. They're close. We just need to solve for x, y, and z. So the first one would be x is equal to 1 plus 2t. Y is equal to, I just hate starting out with a minus, so I'd say 4t minus 2. They're going to say minus 2 plus 4t. It doesn't matter. And z would then be 4 minus 4t. Those are the parametric equations they want because this gives your variables here in terms of your parameters here. Right? That's the parametric equations. Now let's do the symmetric equations. Remember how that went? Start with the same ones we had before and just divide by first 2, then 4, and then negative 4. Okay, what does that give us? That gives us x minus 1 over 2 is equal to y plus 2 over 4 is equal to, now I don't like having the minus there, so I would write this as 4 minus z over 4. I know they don't like it that way, but that's how I like it, just easier to write. You just divide by your coefficients of t. That's why I like starting with these. It's easy to get this, it's easy to get that, both ways, okay? And then set all the t's equal to each other. X minus 1 over 2 is equal to y plus 2 over 4 is equal to, I just don't like the minus sign, so I flip this and flip that, and it's 4 minus z over 4. Well, let's see. Yeah, that's this problem. Let me erase, well, let's just see. Yeah, here they do it. X is equal to 1 plus 2t. Yes. Y is equal to minus 2 plus 4t. I told you they were going to do it that way. I said 4t minus 2. same thing. And z is equal to 4 minus 4t. That's exactly what we got here. Then, for their, because a, b, and c are all non-zero, the symmetric equations can be written as y minus 1 over 2. That's too hard. Is equal to y plus 2. X minus 1 over 2 is equal to y plus 2 over 4. That's equal to z minus 4 over minus 4, which is 4 minus z over 4. Those are your symmetric equations. Okay? Now, they just wrote them down as if they're magic. I find that's easier, or it makes more sense to me to do the x minus that is equal to the multiples of these. That just to me is just the easy way to do it. And it's easy to get these and easy to get those. Okay? All right. Make sense? All right. Planes in space, I don't think we have time to do. Wait a minute. We did example 1. Whoa. There's an example 2 they don't have on the slide set, and then they get into planes in space. So we'll start next time at example 2, top of page 788. Okay? Let's see if we got far enough for any homework exercises here. This is a long section. Okay, I know you can do 5. And I think you can do any of the odds 7 through 11. And by the way, 5's at Calc Chat, 7 through 11 are at Calc Chat, but 9's at Calc View. Then you can do either 13 or 15. They're both at Calc Chat, 15's at Calc View. And I think you can do any of the odds 17 through 23. They're all at Calc Chat. And I think you should be able to do either 25 or 27. They're at Calc Chat. Now did we do parallel lines? I don't think so. But you should be able to, I hope maybe figure those out. Give those a shot, 29 or 31 or both. And you might, I think you probably should be able to do the points of intersection, 33 or 35 or both. And then I think you should be able to do 37 and stop there. After that, we're into planar stuff, planes in space, the equations of the plane. So we'll stop there. Try to do those others. If you find them a little too bizarre, I mean, use calcchat.com. That should help you. Okay. We'll pick up in planes in space next time. Good deal. Good class. And we grew. Okay, 2 more students. Nice to have you. I was thinking this is going to be one they might gripe at me because there weren't enough students, and now we're up to 6 students. That's great. They may still gripe, but they can get over it.